The third fact that moving charges create magnetic fields leads us, again, through experiments and observations, to the conclusion that a current I in a length increment delta L, and that delta L has a direction, so that I delta L is a vector with some direction in space, that the contribution of this current in this length to the magnetic field at another point is equal to what? K prime, just a constant that we'll talk about in a second, times I delta L cross the unit vector in the direction from the segment delta L to the point at which we're calculating the field. And that divided by r squared. It's a reciprocal with the square of the distance here, and also multiplied by the sine of the angle between the I delta L and the r vector. So it's not exactly an inverse square law, because it depends to an extent, to a large extent actually, on the angle of this vector with the delta L. And that's all taken care of by the cross product. K prime, well, magnetic field is in Tesla. So K prime has to have units of Tesla times whatever it takes to cancel out the units of all the rest of this. The units of all the rest of this, delta L is in meters, r squared is in meters, so we have reciprocal meters. I is in is in amps, coulombs per second, but amps. So we have amps over meters here, so that K prime has to have units that involve meters over amps. So it's Tesla times meters over amps, so that the meter here and the meter squared here cancel out the meter here, and the amp here is canceled by this, leaving us Tesla for the units. To calculate the total magnetic field at a point due to the entire current, of course, then we have to integrate an expression that comes directly from this expression. We have to integrate I dl cross r over, etc., with respect to position along the path of the current. And that's going to lead us to a line integral. But right there's the basis for your line integral. The other thing we want to understand is that this is a current, which is a collection of moving charges. A collection of moving charges, well, an I delta L, where I is a bunch of moving charges, it's the rate at which charges move actually, is equivalent to a single charge times a velocity. So that if we have just a single charge, we can replace the I delta L here with QV. Now, I'm not going to elaborate on that, but we could put a QV in here and have the formula for the contribution to the magnetic field of a charge passing a given point with a velocity in a given direction. Okay, and if we have a lot of charges, of course, we can superpose all those fields and calculate the total field in some way, usually by an integral. Now in class, we set up this integral for a long charge, well actually for a line charge, a finite or an infinite line charge, and we set up the corresponding integral for the field due to a loop of charge at the center and on a point in the central axis. And there are many other configurations in which we could set up the appropriate line integrals to calculate magnetic fields.